Hello, this is part 2 of Eigenvalue decomposition. So one of the things that is useful about diagonalization is the calculation of powers of a matrix. And when we say powers of a matrix, what we mean by power of a matrix is that the matrix is multiplied by itself. Okay, that would be a squared is a times a. A cubed means that this is a times a times a. You could also think of a cubed as a times a square, and so on, right? So this requires matrix multiplication is by no means raising all the entries to a given power. You have to carry out that iterative matrix multiplication. So, but one thing we'd like to note is that if we're multiplying, say, a diagonal matrix, so I'm gonna make sure we're in the same page here. So let's say we have lambda 1, lambda 2, and lambda 3. For example, this is a diagonal matrix that is 3 by 3, and let's say this we multiply this by itself. So there are a few ways of calculating this matrix multiplication. So we can multiply the matrix here on the left times the first column, that gives the first column of the new matrix. That matrix on the left times the second column, that would be given the second column. Or we could do matrix multiplication by multiplying each row times each column. So for example, let's take a look at here row 1 and column 1. So if we multiply row 1 and column 1, then we will obtain lambda 1 times lambda 1, which is lambda 1 squared, plus 0 plus 0. So that would be entry 1 1 obtained by multiplying row 1 and column 1. If we now multiply row 1 by column 2, that would give us 0 plus 0 plus 0, which is 0. Row 1 by column 3 gives us lambda 1 times 0, which is 0, plus 0 plus 0, and that gives, this is how we obtain the first row. Now multiplying row 2 by column 2, that would give the entry on location 2, 2, and that would be 0 times 0 plus lambda 2 times lambda 2, so that would give us lambda 2 squared plus 0. Okay, and if we multiply row 2 by column 3, we obtain 0, and if we do the same by column 1, we obtain another 0. And then multiplying, say, row 3 times column 3, we get 0 plus 0 plus lambda 3 times lambda 3, which is what gives us this entry here, which is lambda 3 squared. And so it's easy to see that the other entries are 0. So multiplying, we can now think of this product here as a matrix lambda multiplying another matrix lambda for the particular case of 3 by 3 matrix. And this is a matrix that is still diagonal, all right? And it has the entries on the diagonal are square. Okay, so we can write this as a matrix lambda squared, and what we mean in this case is indeed when you take powers of this diagonal matrix, that is the same as raising the entries to that power. That only is true in general for matrices that are diagonal. For matrices that are in general not diagonal, calculating the nth power, calculating a to the n, is a non-trivial operation. So let's suppose that we have a matrix that is diagonalizable. S is the matrix storing the eigenvectors, lambda stores the eigenvalues. So the power a squared can be computed as multiplying a by itself, but we can represent a as s times lambda times s squared. So here this portion represents a, and so does this other portion. So the cool thing about doing this is that now in the middle we're gonna have s inverse and multiplying s. That becomes the identity by definition of an inverse matrix, and then we're left with lambda multiplying lambda, which is lambda squared in the sense that we just discussed. This lambda is a diagonal matrix, and so multiplying by itself causes the eigenvalues to be raised to the second power. And so now we find that the second power of A also has this diagonalization where the matrix in the middle is a matrix storing the second powers of the eigenvalues. Okay, so if we imagine what happens if now we multiply everything here by A, for example, everything here multiplied by A. So we could repeat that analysis, substitute A by S lambda S inverse. And well, this is emphasizing that when we write lambda squared, we mean a diagonal matrix that has zeros off the diagonal, and it has the diagonal entries as lambda 1 squared, lambda 2 squared, all the way to lambda n squared. Okay, so the idea with the kth power, as I was mentioning before, what would happen if we multiply a squared times a? So A is, as we computed before, S times lambda times S inverse, and A squared is given by S times lambda squared times S inverse. So we could very easily simplify S inverse times S, and this leads to S times lambda squared is lambda cubic, or to the third power, and this multiplies as inverse. So we could easily write a proof using mathematical induction. If you're not familiar with mathematical induction, that's okay, but the idea is that you would see a pattern, right? So now I could take this, so we just found that a to the third power is S times lambda to the third power times S inverse, and I can multiply this by A again. So if we were going to do that, A times A to the third power, this would be A to the fourth. Okay, and by using diagonalization, once again, this S inverse S becomes identity. So in the middle, we end up with lambda times lambda cube, and that leaves us to, that gives us lambda to the fourth. There is S on the left side, and then there is S inverse on the right side. So we're seeing a pattern here where we have A to the fourth power, and that power applies to the diagonal matrix, to the eigenvalues, the so-called eigenvalue matrix, and it's very easy to raise a diagonal matrix to that power, because all you have to do is to raise every single entry on the diagonal, just similar as we had here. If this were to the power fourth, everything here on the diagonal would be raised to the fourth power. So in the spirit of generalizing this result, right, so we'd like to express A to the n or A to the k, then we're going to write something like this. The kth power of A is given by S, the eigenvector matrix, times lambda k, the kth power of the eigenvalue matrix, times the inverse of S. And so the cool thing is that this could be used for calculating powers of a matrix, even though all we're doing is exploiting the powers here of the eigenvalues, right? So this matrix is a diagonal matrix, it has a lot of zeros, and all we need to do is to compute the kth power or the nth power of the eigenvalues, and this would provide us with some useful information. So one thing worth mentioning here is that when these powers are large, sufficiently large, this means, I don't know, k equals to 100, or k equals to I don't know, a number like this, right? 10,000. So when k starts growing towards positive infinity, being positive integers, an important thing to remember is that whenever an eigenvalue has modulus less than 1, then basically this is saying that if lambda j is less than 1 in modulus, then lambda j to, say, the k this goes to 0 as this value of k goes to infinity. So this complex number would converge to 0 whenever its modulus is less than 1. And that's something that we could see an application, an illustration of this. So we have a matrix here that has nice properties, because if you add up the entries on each column, so this would be 0.8 plus 0.2, this adds up to 1. And the same is true for the second column. Such matrices are known as Markov matrices. So we could write this matrix, this Markov matrix, in terms of its eigenvalues and eigenvectors. So this is the diagonalization. We can see how the eigenvalues appear listed here. They appear listed in the diagonal of the matrix that's in the middle. And so the important thing is that now if we wanted to compute the kth power of this Markov matrix, all we have to do is to raise the eigenvalues to the kth power. We can see that 1 to the k it's going to converge to 1. So when k gets larger and larger, really what drives something here is that 1/2 to the k is going to be converging to 0. So when the k power goes to infinity, 1 to the k becomes 1, stays as 1. That's where this entry comes from. And then we obtain that 0.5 to the k becomes 0. Then we can multiply these three matrices together, and that leads to this matrix. First column 0.6, 0.4, and the second column is identical. Okay, so this question here is asking about convergence to the matrix of zeros. When does a to the k converge to the zero matrix? And that happens whenever all eigenvalues are strictly less than 1 in modulus. In this case, one of them was exactly equal to 1, and then we would not converge in that case to the zero matrix. Here we have an illustration. This matrix looks very similar. It's not quite Markov. The second column, though, is 0.5 plus 0.4 is 0.9. We compute the eigenvalues. Now we have, here we have 0.94. This could be considered lambda 1, and this one over here could be considered lambda 2. So it's easy to see that in modulus, here at absolute value, both of them are less than 1 when we raise the eigenvalues to the kth power, right? So we're raising, taking the kth power of the matrix. That means raise the eigenvalues to the kth power. These numbers are going to 0 as k goes to infinity, and this leads to the result that the limit as k goes to infinity of the kth power of the matrix, that limit equals the zero matrix with 2 rows and 2 columns. So in this example, we could diagonalize this given matrix to find an expression, a formula for the kth power. And here, basically what the motivation is to prove such formula. And so we can achieve this by finding out that this matrix has eigenvalues lambda 1 equals 5, lambda 2 equals 4. We have to compute the eigenvectors, compute the inverse of the eigenvector matrix, but we could express, we could diagonalize this matrix A as it follows here. And so when we compute the kth power, we have this. So what we need to do then next is to we need to compute the matrix product. So we would have to multiply these two matrices together. When we do that, we obtain this matrix here, and then we multiply that matrix by this matrix with column 1, 0 and 1, 1. And when we do the last step, we find we arrive at this 2 by 2 matrix that has first column 5 to the k power 0, second column first entry 5 to the k minus 4 to the k, and the second entry is 4 to the k. So this example is a little more elaborate. I went quite fast here to the steps, but I'm confident that you could pause the video now and you can verify the calculations and verify that this is indeed the case.